Hey, Pranam da pawb. Good afternoon, everyone. Welcome back to the physics session. So this is the second in the series of 4 physics lessons for Catch Up with the Caroline Cymru, and today we're going to cover Newton's laws. Newton's laws is one of the units that is always enjoyable to learn because it's really straightforward, unless you don't understand physics, and then you find you quickly get lost. But we're going to take it slow, and by the end of the lesson, you should hopefully be able to remember most of the content. The content is made up of 7 features, and we're going to start from the top and work our way down. So the first few things we're going to look at in the session is inertia, what that means, how inertia relates to mass, and how mass can affect inertia. Once we have an understanding of that, we'll have a little look at Newton's first law. And notice in bold, it says be able to state it. That's because in bold are the features that higher tier pupils must be able to do. All the rest, everyone should be able to do. Bold means as a higher tier pupil, you should be able to do that. So Newton's first law, everyone must be able to understand it and use it. Being able to quote it is something higher tier should be able to do. The third thing we're going to look at is this idea of forces no longer balanced. And what happens when forces are no longer balanced, and how mass and acceleration and force have relationships between each other, and understand what happens. Okay, let's get started. And the first thing we're going to look at is inertia. And understand inertia is this resistance that an object has to a change in motion. It depends on the mass of the object. So for example, if you've got a massive lorry or a massive longboat, as in the picture on the left, versus a small boat, the one with the larger mass has a larger inertia. So that means it's harder to get it to move, but once it's moving, it's harder to slow it down. So let's have a little bit of a look in more detail. Inertia. If we look at a large boulder, it's difficult to start moving the boulder, but once it's moving, it's quite difficult to stop the boulder moving. So a large mass tends to have a large inertia. So it has a large opposition to a change in the motion. So it resists that change in motion. If we look at a small mass, you'll see the opposite. With a small mass, you tend to see it's quite easy to move and it's quite easy to stop. It doesn't require much force to get it to move. It doesn't require much force to stop it. So again, picture if you want a large lorry versus a small toy car, one of them is easy to get moving, one of them is a lot more difficult to start it moving. Okay, now that we have a bit of an understanding of inertia, let's see how it applies to Newton's first law. Newton's first law helps us understand what happens to objects when the forces on the object are balanced. If you're doing higher tier, you can see on the bottom of the screen, you must be able to remember or learn this series of words, and that is an object will remain at rest or at constant speed in a straight line unless acted upon by an external resultant force. All this means is that if you look at a stationary object, again we'll use the boulder for example, if the boulder is not moving, you could say that the forces acting to the left and the forces acting to the right must be balanced. And if that's the case, what we could do is look at the resultant force that we'd often write FR. So the R stands for resultant, F stands for force. So the resultant force here is all the force acting to the left, take away all the forces acting to the right. So the resultant force is 0 newtons. So there is no resultant force, so the object is stationary. It seems quite straightforward because if nothing's moving, then there's no resultant force. However, this is also true if you look at an object traveling at constant speed. If an object is traveling at a constant speed, it's also true that the resultant force is 0. And why is it 0? It's because if you look at the forces causing it to move in the direction of travel versus the forces acting against the direction of travel, what you'll see here is that the forces balance out. Again, giving you a resultant force of 0 newtons. So again, Newton's first law is an object will remain at rest, or an object will remain at a constant velocity unless acted upon by a resultant force. Good. What happens if this force is no longer balanced? Well, a few things can happen. If we look at a stationary object, it might start moving. If we look at something that's already moving at a constant speed, you might find that it will accelerate or decelerate. And that's when Newton's second law comes in. Again, if you're doing higher tier, you'll need to learn the sentence to help you gain some of those marks. And the sentence is: the acceleration of an object is directly proportional to force acting upon it. Or the way I like to remember it is I'll typically remember the equation: F equals ma, force is equal to mass times acceleration. And then I'd often write that as a sentence where the force is equal to mass times acceleration. So how does this affect an object that was stationary to begin with? So if we look at the blue car, to begin with, the car was stationary. And then if we look at the resultant force, we'll see that if you've got 1,000 acting to the right in the direction of travel, but you've got 0 to the left, the resultant force is 1,000 newtons. That means there's a greater force in one direction, so the car is going to begin to move to the right. But when I say begin to move, what type of word best describes the motion of something that's beginning to move? And hopefully the word you are thinking of is accelerate. So this is an example of a car that would begin to accelerate. And we can look at acceleration in a bit more detail. So again, the blue car from stationary, as long as the resultant force is greater in the direction of travel, it will begin moving. A similar thing can happen with a car that's already traveling at a constant speed. If the force in the direction of travel increases, so for example here, the force is now larger in the direction of travel, this means the resultant force is now 800 newtons to the right, which will result in an acceleration. The speed will increase. So go from whatever speed the car was at to begin with to a new higher speed. And the third way we can apply Newton's second law is looking at what happens to a vehicle if the resultant force is in the opposite direction. So here you swap them round. The greater force is against the direction of travel now. And if it's against the direction of travel, this means the vehicle will decelerate. So be careful, because you can see the force is against the direction of motion, but does this mean the car will suddenly change direction? It doesn't necessarily mean it will change direction. What it means is the force is acting in this direction, so the car will decelerate, its speed will decrease, but it could still be traveling to the right. Good. So Newton's second law, you can have a lot of descriptive content to go with it, but at the same time, Newton's second law is the one with the equation, and it's fun to use that equation to help us understand what's going on. And again, the equation is force is equal to mass times acceleration. You can write it in symbols or as a word equation. And if you're doing higher tier, be able to rearrange the equation. If you're not doing higher tier, be able to use them if it was given to you in a question. So they give you the equation, you'd have to be able to use it. Higher tier, you would use the equation and rearrange and then use the equation. Okay, a simple example, a very, very simple example is: what value of force must the van experience if it is to accelerate at a rate of 4 meters per second squared if the mass is 2,000 kilograms? There's 3 options. Hopefully some of you might use the chat function to put the answer in, and you can then have a good idea of if you're right or wrong, but obviously I'll have to give it away because of the delay in the recording. And the answer is 8,000, but look at the technique used here, the 3 simple steps. F equals ma. So the first step is identify the equation. So if you sit tests and exams, you should have the list of equations, and identifying the equation would be the first step. The second step is correctly identifying the numbers. So in this example, the numbers given are the only two needed. However, sometimes you might find questions have more information needed. So what you would do then is you would check the units. Make sure mass and meters per second squared are the numbers you are looking for, the units and numbers you need. And then the last step is always, can you use the calculator or can you do mental maths? Good. So we've seen Newton's second law now, descriptively and in an equation. The final thing to do is possibly look at how does Newton's second law change depending on the mass or the force. And that's one of the big questions that you can sometimes get, is to understand how Newton's second law is influenced by other factors. And this is one of those big ones where a lot of description goes into it, because just like in school when you've done experiments, you always have to keep one thing the same, change the other, measure the other. Remember this concept of variables, where you have a control variable, an independent variable and a dependent variable. We can apply this here to have a look at what happens if you change the force. So what we're going to do is quickly try and understand Newton's second law better by looking at acceleration. And to look at how acceleration is affected by force, we must keep the mass constant. So that's what we'll do. First step is, let's look how force affects acceleration. So we have three identical cars of identical mass, but we increase the force. As the force increases, we can calculate the acceleration each time. And what you notice is there's a pattern. Hopefully you can see the pattern. The acceleration increases. So going from the first car to the second car, the force is doubled. And you can see the acceleration also doubles. Or going from the first to the third car, you can see that the force is tripled. And what you see is the acceleration also triples. So this is a good example to demonstrate that acceleration is directly proportional to force, which is one of the definitions we are meant to learn from Newton's second law, and that is that acceleration is directly proportional to force. And it's quite straightforward to see from this picture, because when you go from 200 to 400, you double, you times by 2, and the acceleration goes from 1 to 2, which is a double again. So what you can see here is, as force increases, the acceleration increases at the same rate. And this is how we understand directly proportional. If I was to multiply the force by times 4, you'd expect to see the answer for acceleration to increase by times 4. Or even if I times the force by 40, you'd see the same thing for acceleration. So this is what we mean when we say directly proportional. We could do the same thing for mass, but if we do it for mass, hopefully again some of you might be using the chat, what would we have to keep constant to have a look at the effect of mass on acceleration? Good, hopefully someone's managed to put the answer in before I've given it away, but if we change the mass, this time we will have to keep the force constant. And again, calculate the acceleration, but this time notice the acceleration is decreasing. So when the mass doubles from 200 to 400, the acceleration decreases by a factor of 2. So there's a divide by 2 this time. Or when the mass is tripled, the acceleration drops to a 1/3 its original value. And this is a nice way to understand that acceleration is inversely proportional to mass. What this means is, as mass increases, the acceleration decreases, but notice the rate is the same. So if it's times 2, it's divide by 2. If it's times 4, you'd expect it to be divided by 4. And again, I could write times 40, and I'd expect it to go down by divide 40. So we could put all of this information together now to fully understand Newton's second law, and that is acceleration is directly proportional to force, but acceleration is inversely proportional to mass. And that is one of the statements you should be able to remember. let's have a look at what we've covered. So the first 15 minutes now, we have gone through the concept of inertia. The mass is an expression of inertia of a body. So we understand that something that has a large mass has a large inertia, and it's typically hard or difficult to get it to start moving. And once it's moving, it's difficult to stop it from moving. It's difficult to change its motion. The second thing we've hopefully covered in enough detail now is Newton's first law, and be able to state it. So Newton's first law is to do with the forces being balanced, and if you state it, you would state it as an object will remain at rest or at a constant speed unless acted upon by a resultant force. So you understand those little diagrams where for Newton's first law, the force to the left is equal to the force to the right. So 1 Newton, 1 Newton. So the overall resultant force is 0 Newton. So this object could be at rest or at a constant speed because the resultant force is 0. The third thing, and probably the most recent one, is how unbalanced forces produce a change in the body's motion. So we understand that you get acceleration if the resultant force is to the right and it was already moving to the right. You might get deceleration if the resultant force is in the opposite direction of motion, or if the object was stationary, it would begin to move. So I think we understand that now. And the next bit is the long wordy section that we just saw, that acceleration is directly proportional to force and inversely proportional to mass. Good. And the bit in between is Newton's second law. So being able to use force is equal to mass times acceleration, and then as highlighted here, being able to say that acceleration is directly proportional to force and inversely proportional to mass. And that covers the first section or the first part of our Newton's law session. The next part is going to cover 5 and 6. We're going to jump into the differences between weight and mass, understand how Newton's laws help us understand what weight and mass are and how they're actually different, and you should always be careful when you use those words. And the next section would be looking at terminal speed and what that means when we apply forces to objects falling in the air around us. So let's begin. Weight and mass. So what you can see here is the same astronaut has gone on a journey from Earth to the moon. Notice how the mass has remained constant throughout. So mass is a feature that doesn't change depending on what planet or object you happen to be on. So mass will remain constant. It's the amount of matter an object has, whereas weight is a force. And you can see that because if you look at the units, mass is in units of kilograms. However, weight is in units of newtons, which is a measure of force. So what we have here is weight is a measure of someone's mass acting within a gravitational field. So for example, on Earth, the gravitational field strength is 10 newtons per kilogram. What this means is a 1 kilogram mass would be pulled downwards by a force of 10 newtons. And we can represent it as an equation. And this equation is really similar because weight is a force, mass is mass, and gravitational field strength can often be seen as the acceleration. So here, when you see the weight equation, I often think it's actually just the same thing as Newton's second law. It helps us understand the force because of the acceleration you would experience on Earth. And we can test this now, guys. We can test it out. We can have a little look. If this is true, the astronaut's mass is 100, and we can find out would the weight, so the force or the weight, actually be equal to 1,000. So we can check if the mass is 100 and on Earth the gravitational field strength is 10, what we get is 1,000 newtons. So that's quite a nice question, and it does check that the weight should be 1,000. Good. The other thing that comes up in this unit is as a higher tier pupil, ability to rearrange the equation, and that's what we can have a go at now. So we can actually look at the information given here. The information given here gives us the mass and the weight. For some reason my pen keeps jumping, so it's not making a box. So what we have here is the mass and the weight. Using this equation, we could calculate the gravitational field strength. So if I write the equation in symbols to make it easier and more clear to rearrange, we can actually try to calculate that gravitational field strength on the moon. Because if you rearrange, hopefully you're following along, you would have W divided by M, which would give you 162.2 divided by 100, and you would get an answer of 1.622 newtons per kilogram. And again, my pen is moving the ink around. Good. So here, higher tier, you've rearranged. If you were expected to do this in a foundation tier, you would be given this equation to begin with. Don't need to learn it because you should be able to rearrange as a higher tier pupil. So weight and mass, very straightforward, I hope. However, we get to look at terminal velocity now. So as I just said, your mass always stays the same. Your weight is what changes depending on what planet you're on. And for the terminal speed, we're going to consider that we're on Earth. So because we're going to consider we're on Earth, we can straight away remember, well, actually, on Earth, the gravitational field strength is 10 newtons per kilogram. So that is constant. So if we're on Earth, the weight of a skydiver is going to remain constant. And if we wanted to use an easy number, if we used the mass as 100 kilograms, we could say the weight is 1000 newtons. So looking at the skydiver, you can see I've got several bullet points, and we're going to look at the journey a skydiver takes to land safely on Earth. And this is one of the points within Newton's laws that often comes up as a big extended writing task. It's always a nice one because it demonstrates your knowledge of all of, well, the first two Newton's laws, and it really pushes you to explain it clearly. So we're going to look at it here in step by step, and then we'll look at how to answer it on the next two slides. So first of all, the skydiver initially jumps out of a plane. The only force that has a significant factor to begin with will be the person's weight, and this weight is obviously acting down, and it will be a constant value because this person's on Earth. That weight will remain constant, and because they've just jumped and that the resultant force is downwards here, you know that the direction of travel is going to be down and the person's going to be accelerating. So the speed is going to be increasing. As the speed increases, what you'll notice is this person will travel through the air or through air particles more and more per second. So this means as the person's speed is increasing, they are hitting more air particles per second. And what this means is this person will experience an air resistance, so a resistive force against this person's motion, which will result in a resultant force that will still be downwards. However, it will be less than when they first jumped out of the plane. So this person is now not increasing in speed as much as the first point. If this person's speed is still increasing though, what you'll see is over time, the air resistance will reach a point where it will be of the same size as the person's weight. And this is what we call terminal speed. We call this terminal speed because what you notice is if you work out the resultant force, you should find that it's 0 newtons. So right here in step C, the force acting down, the person's weight, which hasn't changed since they started skydiving, has remained constant. The air resistance has increased the entire time they have fallen until the two balance out. So there's a lot of information in bullet point C, because if resultant force is 0, you should hopefully remember that Newton's first law has a good description for what happens when the speed is 0. And what you could say is that in this stage, you could quote Newton's first law in your answer, which would be an object remains at rest. In this case, it's not at rest. So you would say an object remains at a constant speed unless acted upon by a resultant force. So here we have a resultant force of 0. This shows the skydivers reached terminal speed or terminal velocity. So the only thing that's going to change this now is if there's a change in the force, in the resultant force on the person, and that can be done by opening the parachute. And what you'll notice, if you open the parachute, notice the size of the arrow acting up, means that the resultant force is upwards. And what is actually going on in this picture? Well, what is actually happening in this picture is the air resistance upwards is greater than the weight downwards because the parachute has opened, which has increased the surface area, allowing a lot more air particles to rush into the parachute. Good. Will this result in the skydiver decreasing, increasing, or staying at the same speed? I hope you're all following along, because this will mean the person's speed will decrease. But remember, it doesn't mean the person's going to change direction. Just because the resultant force is now upwards, the skydiver is not just going to suddenly fly upwards. What will happen is the speed will decrease. They'll go from a very fast speed and the speed will decrease. It will keep decreasing until the size of that air resistance is of the same size as the weight again. And this time, the forces will balance out again. So what we'll have here is a resultant force that is equal to 0 newtons. And what's so good about this is that for a resultant force of 0 newtons in this case, the terminal speed will be much lower than in the first case without the parachute, and hopefully the terminal speed with the parachute open is low enough to safely land. Okay, that was quite a lot to take in for terminal velocity because it is one of those big 6-mark questions. But what we're going to do now is quickly put up on the screen the first sentence, so hopefully you can build up an answer as we go along. Some of the answers are in this terminology box, but not all of them, because not all of them count as the terminology. So have a quick think what goes in each gap. Good, so hopefully that's long enough time for you guys to think what should go in each of the gaps. And what we've got here is the start. At the beginning of the skydive, the air resistance is 0 newtons, or you could say negligible, or nothing, or very, very low. So they accelerate. So a nice way to say this is they'd accelerate. You could say their speed would increase, or they accelerate. The second step, what we look at here is, as the speed increases, or as they speed up, the air resistance, and again, I'll do a short pause for you guys to think, or even type in what you think the answer would be. And hopefully, guys, you have a good understanding that as they speed up, the air resistance increases. And then the big one, the big paragraph, this bit comes in here now, with a lot of statements. Read through it and think what you put in here. So hopefully you've got some of the correct answers. Let's find out. Eventually, the air resistance will be equal to the skydiver's weight. At this point, the forces are balanced and the skydiver travels at a constant velocity, and we call this the terminal velocity. So these first 3 steps is the first half of a skydiver question. The second half is then seen by looking at this example here. So the second step, what actually happens? Well, the parachute opens, so the air resistance increases, which decreases their speed. And then over time, what's going to happen? The forces will balance again, and the diver now travels at a lower, and we could say lower terminal velocity, but it's also correct to say it's a lower constant velocity because they are trying to signify the same thing. Good. Hopefully the terminal velocity section has helped you understand the skydiver question. And if we go back to the cover, we can see the two things we've just covered include weight and mass and the difference between weight and mass. So remember now that mass is the same everywhere. However, the weight depends on the planet or the object you're on due to the gravitational field strength. And if you get that, you know that weight is equal to mass times gravity, and you can work out an object's weight. The last thing we just looked at is forces and their effect to explain behavior of objects moving through the air. The concept of terminal speed. And terminal speed essentially is balancing the person or object's weight with air resistance, and trying to remember what happens when the weight and air resistance are equal to each other and what happens when one is greater than the other. Good. We're on to the final law with plenty of time remaining. So let's have a look at Newton's third law, and again, Inertia being able to state it. So Newton's third law is one of those enjoyable ones because it looks at forces acting against each other or on each other between objects. Inertia, this is the definition they look for. So if a body A exerts a force on body B, then body B exerts an equal and opposite force on body A. Let's have a little look in more detail at a book on a table. Let's start in the middle. So let's apply Newton's third law here because the wording of it can sometimes be difficult to understand. So the wording is body A exerts a force on body B. So let's have a look. If we call the book body A, that means the book is exerting a force on body B. So body B will be our table. So we have a book exerting a force on the table, and remember it has a direction, so the book exerts a downwards force on the table, which is seen in that bottom sentence right here. Downwards force by the book on the table. Newton's third law tells us there must be an equal and opposite force. So if we have a downwards force by the book on the table, we must have an upwards force that must be by the table on the book. So it's important to get this right by taking it from the statement. So if you learn the definition, you can apply it to any example given. So for example, let's have a look at a ball that's fallen to earth. So a ball is falling to earth, so it could have been kicked up and it's now on its downwards journey. And let's have a look. If we look at the earth, we could understand that the earth's force of gravity is pulling the ball downwards. So all we've done is apply the first part of Newton's third law. So body A being the earth, exerting the force being gravity onto body B, which is the ball. So body B, the ball, must exert a force on body A. So now this tells us that the ball must exert a force on the earth upwards. So when a ball is falling to earth, it's falling to earth because the gravity of earth is pulling the ball downwards. But have you ever stopped to think that the ball is actually also exerting a force on the earth in the opposite direction? This is why Newton's third law is one of the ones that often gets skimmed over, because it's sometimes strange to think about that the ball is exerting a force on the earth. Good, let's have a look at a rocket in space. So the final one that I can't click. Oh, stuck in the pen. Here we go. So again, we use the law to write the sentences for us. So body A on body B, then body B on body A. And remember, it's equal and opposite in direction. So if we have a rocket being body A, the rocket pushes the exhaust gas out the back back of the rocket. So exhaust gas is body B. So what we've got is the rocket exerts a force on the exhaust gas backwards. So the logic tells us from Newton's third law that the exhaust gas must exert a force on the rocket forwards. So this is why Newton's third law is one of the fun ones, because you take the statement, the definition, and you apply it to different examples. Newton's third law is quite a short one. At the end of it, it helps you understand it a bit more. So let's have a look. With 5 minutes to spare, have we gone through everything? So 1 through to 7, what we've got here is inertia being number 1. We have covered that. Understand that inertia is dependent on mass, and if the mass increases, inertia tends to increase, because an object might be difficult to start moving because it has a large inertia and a large mass, but once it's moving, it can also be difficult to stop that movement. The second thing we've seen in today's session is Newton's first law of motion, and this is this idea of forces balancing out, being able to state it. So what you would state is an object will remain at rest or at a constant velocity unless acted upon by a resultant force. And the third thing we've seen is when those forces are no longer balanced, what will happen is the object will change its motion. So if it was stationary, it'll start moving. If it was already moving, it will accelerate or decelerate. And then we've also seen what happens if you change some of these factors. And what we found was that acceleration is directly proportional to force, and acceleration is inversely proportional to mass. That allowed us to understand Newton's second law, and that force is equal to mass times acceleration. So if you were given some numbers, you should be able to input them. If you were sitting higher tier, you should be able to also rearrange equations confidently. The most recent thing we've covered is weight and mass. So understanding that weight is a force measured in newtons, mass is the amount of matter an object has and remains constant wherever you are, and it's measured in kilograms. You can calculate weight by remembering that weight is equal to mass times the gravitational field strength. And again, higher tier, hopefully you found that rearranging a question example quite straightforward. This gets us to the 6th point, which is forces and the effect to help explain terminal speed. So again, when you see the terminal speed, always think, could I explain a big extended written task? If you could, you break it down into each section, 5 sections. So when you first jump out of the plane, as you accelerate, once you reach the terminal velocity, finally from terminal velocity, opening the parachute, and then finally reaching a new lower terminal speed. And the final thing, the most recent thing we've seen is Newton's third law and being able to state it. So stating that if object A exerts a force on object B, then object B will exert a force that's equal in size but opposite in direction on object A. If that's the case, I think we have covered all of Newton's laws in 39 minutes. Hopefully there's been some questions in the chat. I'm not sure. I hope you have found this useful.
Yeah, there have been some questions, and I've answered them as they've popped up.
Good. Has anything stood out as an issue or anything not as being clear?
Not really, unless there's any other outstanding questions now, kids, you want to ask about Newton's laws. It's a good time to do so. All right, and we're happy to hang on for a second and help you with anything that you have any queries about.
Good. And remember, this lesson and the PowerPoint, as well as all the other ones, will go up on the website roughly a few days after they've been done. So if you're looking for this PowerPoint and the other ones, they'll obviously show up as time goes on. Okay.
So we have a question here. I'll publish it actually. And that is from Sam. Is the maths on the lower tier?
Maths is on the lower tier, but you shouldn't be expected to rearrange equations, just using the numbers and identifying the numbers you need to use.
So looking in the question, so if it says 5 newtons in a question, it's really important that you know that that 5 newtons means that it's a force, all right? And then you know you're putting that 5 newtons where the F goes. And similarly then, if it says 10 kilograms, knowing that 10 kilograms means mass, and then you're putting that where the M would go in that equation, okay? Yeah. Really good, well done.
Oh, another question here. Will you have to state all 3 laws in an exam or test? You won't have to state all 3, but you're expected to know all 3. So what often happens, you might have one year you'll have a paper asking for one of the laws, but then the next year they might ask for the 2 of them, and it just depends on the year of the exam. But knowing all 3 means that whichever one comes up, you've known them all.
And the best version of Newton's third law was the one that Mr. Nettle gave as well, because you see different ones do something, sir. You see the reaction, every action has an equal opposite reaction, and that's okay and everything, but the best version is the object A and object B one.
I think using the object A and B, you can apply it easier, because that's when the marks start to increase, is when you get the questions. Use it to explain a ball falling in air or a rocket in space. Yeah.
And then all you're doing then is where it says object A and object B, you're just substituting in the object. So for example, if you had a propeller on the back of a boat, okay, the propeller's pushing the water and the boat's going forward, and they might say use Newton's third law to explain that. Well, you'd say that, well, object A is the boat, so object A is pushing object B, which is the water, so the boat pushes the water, and then the water pushes the boat with an equal and opposite force. So you can just substitute those in. Really great question, well done. Are there any more questions now, kids? And well done, and you know, it's great that you've attended this, and I know we're back to school next week, aren't we? So I don't know if people are happy about going back to school. I'm sure I'm sure you are. I think it'll be good to get out of the house at very least. I don't know if anyone's got any comments on that, but if there aren't any more questions, then I think we'll probably call it a wrap. I'll just give it 20 seconds just in case any questions do come through, sir, because there is a slight delay, isn't there?
Yeah, there's a good 20-30 second delay, so you're always quite far behind us, guys.
Okay, next week it's space. No, it's not called Stars and Planets is what it's called. I keep on calling it space. So hopefully we'll see you there for that, okay?